In this video we're going to be looking at the computer architectures, and it's essentially the last part of the section on CPUs and architectures. This is quite a short video, so I'm going to just dive straight in. We're going to be looking at specifically the difference between von Neumann and Harvard. Now, although on the specification it does say contemporary processor architecture, it's a bit of a misleading phrase. Actually, what they're really getting at is how the von Neumann architecture is different to modern computers, and we'll kind of explore that later on. In fact, we have actually already done it, but haven't made it really explicit. So, what is a computer architecture? Now, in order for us to fully understand von Neumann and the Harvard architecture, we need to understand what we mean by architecture. So essentially, it's how fundamentally the computer is going to work. It's how the programs can be saved, how all that kind of aspect of it. So number of processors, where they're stored, how they're fetched in the CPU, how the input and output devices connect together, all those kind of things are effectively governing over the architectures. We're going to look at the main ones, which is von Neumann and Harvard. If you are interested, it might be worth having a look at the architectures that came before von Neumann, just see how revolutionary it was when it first came out. Although I'd love to put a little history lesson in here, I don't think it's relevant for this moment in time. So, the von Neumann architecture is something that you'll be very familiar with already. Okay, so as we go through these bullet points, you'll probably start to think, I've heard this somewhere before. So, memory will contain both data structures. Now, this is the one bit that is kind of new. I'm just going to do a little bit of a history lesson, like 30-second one. Before the von Neumann architecture came along, what used to happen was programs would be designed in hardware. So you'd have a program written on circuitry, and that circuitry would then be placed inside the computer. In order to change programs, you'd have to physically open the computer up, take the circuitry out, and put a new one in. This at the time used to take weeks at a time to actually swap programs over, so it was incredibly inefficient. When the von Neumann architecture came along, we had data instructions all stored in the same place, so we can just simply use the FD cycle to actually fetch instructions and start executing them. Now here's where the thing starts to sound a bit more familiar. So FD cycle, we've been talking about the FD cycle already. Uses of clocks to synchronise FD cycles, we've talked about that as well, and input and output devices connected via buses, so we talked about buses as well. So the reason why it's so familiar is that modern computers are based on the von Neumann architecture. And it's very likely that the computer you're using right now, be it a mobile phone or an iPad or even desktop computer laptop, it's using the von Neumann architecture. Okay, so this is why it's so familiar, which is kind of in where the danger lies, because it is so familiar, people forget about those kind of key bullet points. So it's important that you have these 4 bullet points in your note. So let's just kind of explore what we mean by shared memory data. So as you already know, RAM is one big block of space, effectively, of memory. Inside there, we will place the programs that we have loaded up, we'll place the data we're currently working on, and the currently running operating system. It's partitioned by the operating system, not by the CPU. Whenever I read answer which says the CPU partitions memory, I always get a little bit sad. Data for programs like in files will be stored alongside programs. So the operating system would basically decide and has the flexibility on where things go in memory. It doesn't have to say all programs go on one side, all data goes on the other. So it's up to the software, the operating system, to manage that, and it's not down to the hardware to do it. Just a little aside, because we've looked at this already, we already know the von Neumann architecture has problems, because we've been talking about the von Neumann bottleneck. Hopefully now you can start to see, that's why it's called the von Neumann bottleneck. Because we can only fetch instructions one at a time, and data one at a time, we are limited to the speed of the slowest device. So if I'm copying something, if I'm, say, loading and executing a program from the hard drive, it has to copy from the hard drive to memory, then memory into the CPU. which means that I can only go as fast as the hard drive. So I'm waiting for the hard drive to basically send the data over. The CPU ends up being idle for the majority of that process. So as the CPU speed increases, memory hard drive speed doesn't really keep up in the same way. Especially with hard drives is very limited on the bus more than anything else, and it tends to increase in size rather than speed. So we only go as fast as that slow size. So we've got this problem, which is a key problem behind the von-Neumann bottleneck, that we have a mismatch between the slowest and fastest devices in the computer, okay, and we call that the bottleneck. So let's look at the Harvard architecture. Now the Harvard architecture is named after the Harvard Mark I computer, which first piloted this architecture, and it's quite simple. It's very similar in a lot of ways to the von Neumann architecture. The key difference is that data instructions are separated. Okay, so all the instructions are physically stored in a separate block of memory, whilst the data is also stored in a completely separate block of memory. This means that I can fetch an instruction and data at the same time. Think back to when we were talking about the FD cycle, and we were talking about where we have to do additional fetch to run instructions. So let's say an instruction had an address as its operand, which means that I have to do an additional fetch to get that data from that address. The Harvard could do that at once. Okay, so it can execute, it can load up the instruction as it's loading up that data and run it all at once. So we've got this benefit of parallel fetching. So it sounds really good. It also means we have a bit of flexibility. So let's say I only use 32 bits for instructions and 64-bit for data. So I've got a flexibility of how big the bus is for the data side of things and instructions. Some modern computers try and make the Harvard architecture kind of in their own kind of right, where they actually will have a cache separate for instructions, okay, to give a little bit more parallelism, okay. So one thing we need to do is really be clear about the similarities and differences between us. So effectively, the similarities between the von Neumann architecture and the Harvard architectures is pretty much everything apart from that data instructions are in the same block of memory. For Harvard, that's different. Now, it's also important to understand the benefits of the two architectures, because a lot of people might think, well, okay, so if I can fetch data instructions at the same time, surely that's better. Why aren't modern computers based on Harvard? So the benefits of von Neumann is we have a flexibility to allocate instructions and data, which means that the ratio between them can change. Why is that such a big deal? Because we never know what's going to be running on the computer. It might be I suddenly open up a program which has massive amounts of data. Or it could be I open up a program which has loads and loads of instructions in it. Okay? Because of the von Neumann architecture, it doesn't matter. Okay? I can have any ratio between those two things that I want to. With Harvard, I'm stuck. I've got a set ratio between instructions and data, and if I happen to have a couple of programs which are really big in terms of the amount of instructions they have, then I might run out of instruction data memory space. Whilst vice versa, I might have the same for data. Let's say I only have a very small program which happens to use a lot of data, for example, like Photoshop. I might run out of memory on data. Okay, so I have a fixed ratio with Harvard. With von Neumann, I don't. It does also allow the operating system programmers the ability to organize and manage memory as they see fit. So they've got the flexibility there. With Harvard, the key here is things can happen in parallel. We have a little bit of flexibility in the bus sizes that I can use. And that's really the core benefit of Harvard. One of the reasons we don't use that is because we can kind of simulate some of that parallelism just through clever processor design, but also because of that lack of flexibility, it means that we could have a situation where there's loads of spare space in the instruction block of memory, whilst in the data block of memory, I'm having to use virtual memory. I'm having to swap things in and out, and it would ultimately slow down the computer. So Harvard isn't great when it comes down to more general purpose computing. It is, however, really good for things which the size of the program is known in advance. So, for example, like DVD players and embedded software, you'll probably find that Harvard architecture is very common in that type of device. So just to kind of finish off, this is coming back to the statement contemporary processors. What you need to know is what's the difference between the von-Neumann and contemporary computers. Okay, in essence, they are the same. Okay, so modern computers use the von-Neumann architecture. However, because of the von-Neumann bottleneck, we need to find ways of getting around it, and we've looked at these ways already. Okay, so having multiple cores, being able to run more than one process at the same time, using caching. And there are other ones out there, so I've put one other one on here, hyperthreading. There are other enhancements. You need to know about cores and caches. Okay, they're the two core ones. Sorry to use the word core. They're the two ones you really need to know about. If you're interested, do have a look at some of the other ways CPUs can improve performance. So here's a task for you to have a go at. Discuss which architecture you think next year's computer should be based on. So the core idea behind this question is really to think about, okay, which architecture is better and why. Okay, I've put a little word cloud underneath just to give you an idea of some of the things you might want to kind of include into it. So thinking about data instructions, that difference between them, parallelism with the Harvard architecture, buses, the flexibility of von-Neumann, the bottleneck, and ways of overcoming it, cores and caching. So this question is really getting you to bring all of the three elements of this lesson together in one answer. Okay, make sure you're looking at both the pros and cons of both architectures before you give your own opinion of it. Okay, now when you're answering this style of question, as long as you've got evidence to back up your opinion and it's well argued and well formed, it doesn't matter which one you choose. Okay, it's not one of those there is a correct answer. It is here's the facts, here's you applying those facts to the problem, and then there's evaluation at the end of it. You will get very used to this style of question as time goes on. Okay, but just kind of summarize how to answer this question. Give me some facts, apply the facts back to the problem, and then give me an evaluation at the end of it. And just to finish off, some subject clarification. Candidates need to have an understanding on the von-Neumann and Harvard architectures. Candidates should be aware of the different approaches the architectures takes to storing instructions and data in memory and the benefits of each approach. Candidates will not be asked about specific aspects of contemporary process architecture unless explicitly named in the specification, i.e. cores and cache. Candidates may, however, be asked to show an awareness of how contemporary processes differ from a pure von-Neumann architecture in more open questions, i.e. von-Neumann architecture doesn't have multiple cores, it doesn't have caching, whilst modern processors do. Okay, so that's really a good clarification to make on what you need to be able to do and understand for this topic.